Okay, hi guys, and this is another coding video, and I wanted to go through this 2025 British Informatics Olympiad round 1 question, and it's a palindromic sums question. So let's just go ahead and read it, saying every positive integer can be represented by a palindromic sum of at most 3 palindromic numbers. That's numbers that remain the same when the digits are reversed. To be a valid palindromic sum from an integer, the sum must contain the smallest possible number of palindromic numbers. It can contain duplicates. For example, and then we've got these examples here. 1, 2, 3, 2, 1 is a palindromic number already, so it can just be formed from 1, 2, 3, 2, 1. 9, 6, 10 is equal to 1, 6, 1 plus 9, 4, 4, 9, which is the only pair of palindromic numbers that sum up to 9, 6, 10. And there can be triplets that sum to 9, 6, 10, but those contain too many palindromic numbers. Right, so what I think it's getting at is, like, we have two possible ways of representing 9, 6, 10, but we want it with the smallest possible number of palindromic numbers. And then here at the bottom we've got 1031 needs 3 palindromic numbers. So we've got 2, 494, 535, and 488, 939. That's just two possible ways. And then here it says, write a program that reads in an integer and outputs 1, 2, or 3 palindromic numbers which together form a minimum length palindromic sum. Okay, for this video, I'm just going to go ahead and do this main question 1. So the first idea I've got from this first line is 12,321 is a palindromic number already. So I guess the first thing we can do is check whether a number is actually palindromic. I've gone to Visual Studio Code and I've just created a folder, just a random Python folder. I'm going to be doing this in Python. First we can just, I guess, define a function. We can call it, I don't want to do it long. Okay, fine. I'll just do palindromic. And then we can pass in n, which is the integer that we want to have a look at. And the first thing we want to say is, well, is the number we've inputted, is it a palindromic number itself? If it is, then we don't actually need to do anything. We're done. So we can just go ahead and say, well, I want to turn this into a string. So let's just say s. Let's just call it string. String equals string of n, right? And then below that, we want to check whether it is the same when reversed. So we can just use some slicing to do that. We can just say return. We want to return this function if s is the same as s when you reverse it. And this here is the syntax to reverse it. You're just going from the start to the end -1. So you're stepping back through the string you've got. You're stepping back from the last element and you're just going back to the first one. And also just make sure this is string, by the way, not s. Now, one of the things I didn't mention actually is that you cannot kind of just do whatever you want, really. You have to make sure it's less than 1 second. So this whole thing has to be less than 1 second. So I actually have to we gotta try and actually optimize this a little bit. Okay, so I think the next thing I want to do is I want to generate a list which has all of the palindromes less than n. And I think I can do that using list comprehension. So if we go back here, I'm just going to change this to is palindrome. And I can go below and just make a new function. I'm just going to call it, I'm going to let this be the main body of the code, which is going to check for our palindromes to see whether it's made of 2 numbers or whether it's made of 3 numbers. So I can just call this palindrome decomposition, I guess. Yeah, that's fine. And I'm just going to go below and I'm going to say if is palindrome from the function we made above. And I'm going to make sure to pass in n. And if it is, I'm just going to return already a palindrome. And I'm going to pass n here to the top as well. And essentially what this is going to do is just going to take our number. Is it the same? Is it a palindrome? Is it the same when you reverse it? And then we're going to go down here and say if it is, then we are just going to return. I'm just going to say that's it, we're done here. So yeah, I was saying I want to do some list comprehensions and I want to check, I want to create a list of all the palindromes that are less than n. So to do that, it's actually not too bad. I can just do palindromes, if I can spell it. is equal to the list comprehension I for I in range. And I can just go from 1 to n. So I can just go from 1 all the way to the number we've inputted. And then after that, this list is only going to contain elements if is palindrome. Let me just pass in I. So essentially what this is doing is just creating a list which contains all the palindromes from 1 to n. This list comprehension, you could do it procedurally, you could just do it line by line. That would look something a bit like this. But for this case, what you can do is you can just say, I'm going to loop through all the numbers going from 1 all the way up to n. And I'm only going to put it in this list if it satisfies this. I'm only going to put it in this list if, when you reverse it, it's the same, i.e. it's a palindrome. So we're creating a list containing all the palindromes that are between 1 and n. So the next thing we want to do is, well, obviously we want to see if it can be made up of 2 palindromes. So I think I'm going to separate my palindromes. I'm just going to call this 2 PDs. And then down here, I'm just going to call this 3 PDs. So I can just do different blocks of code for each one of them. So here I need to check whether n can be split up. Before we go on, I just want to actually really quickly jump back just below here. And I just realized if we can turn palindromes into a set, that's going to make the processing time go from O of n to O of 1. So because we have this whole thing where it has to process in less than a second, we can just save some processing time by putting palindromes into a set. So we can just say pal set, palindrome set equals set of palindromes. This back here is O of n, but this operation will be O of 1. It's constant time. So that's just a little trick that can save us some processing time. It's extremely highly needed, I think, because we are trying to literally cut down as much time as possible. The way it works is you get marks for each test case you pass. So there's going to be like very small test cases which should work even if you have like a ridiculous time complexity like O of n squared or O of n cubed, or let's say just matter of example O of n factorial. But when you get higher and higher, you get more marks for passing the tests which are harder to pass, so the ones with the larger input, so with larger values of n. So right here you can see that you're getting these marks for 1031 and 1 and 55, but then you go over here, you get 2 marks for the, well, from here you get 2 marks onwards, and this is probably the hardest one to pass. It's a massive number and it has to be split into 3 palindromes. So when you were saying we want to like cut down the time, you really want to cut down the time so you can get these 2 marks by allowing this to process in less than a second. So now we can go down here. I just want to check, to do this, I want to decompose n into 2 palindromes. For p in palindromes, if n minus p in pal set, we can return p n minus p. So what's going on here? For p in palindromes, we're looping through each palindrome in the list. If n minus p in pal set, so let's just assume we have 1, 2, 3, 4, 5, 6, 7, 8. These are all palindromes. All single digit numbers are palindromes. So if we have n is, I don't know, 500. If n minus p in pal set, so 500 minus 1, let's start with p equals 1. 500 minus 1 is 499. If this is in pal set, which it will not be because pal set is made of palindromes, then we're going to return, down here, we're going to return p, which is 1, and the number which we just found, which is 499. Of course, this would never happen because 499 is not a palindrome, and this has to be made of both of these being palindromes. But you can see the thought process. It's going to keep looping until it finds a number where n minus p is in pal set. So that means p is a palindrome because we specified this from the list. And n minus p is in pal set. This is the condition that we have to pass. And once we pass both of these conditions, then we can put together these 2 and we can say this is the decomposition of this number here. And the good thing is we don't have to worry about size or anything because palindromes in itself is going from 1 all the way to n. So we will have the smallest results before we get any of the bigger results. So as soon as we get a result, we know that is the smallest result. So now this is checking for 2 palindromes. We can just go ahead and actually run this. We can say result is just palindrome decomposition, and we can just put in what's one of the examples they give us here. It's 1031. No, actually, let's see. We have to see one that decomposes into 2. So 894. We can go and run that, and there you go. We can see straight away we've got in our output, we got 606 and 888, and that was rapid. 6, 888, and of course 6 plus 888 is 894. So that passes. We could try it again for this one, 21,802, and we'll see what we get. Boom, it's so quick. It's 10,901, 10,901, and there you go. 10,901, 10,901. And we would get 2 marks for each of those. So we'd have 4 marks at that stage. We've got 2 palindromes working, but we want to do 3 now. So this is going to take a pretty similar approach, but there's going to be one key difference. We need to find, let's just say we're given a number, we need to find the pairs such that you have x, y, z. So what we can do is we can find x, and then we can minus x from this number here, and then we're just doing the same thing as we did back here, but for 345 minus x. So that's it. We just need the main bulk of what we need to do for free palindromes is just calculate what is our x going to be. Like we said, we need to find our x. To do this, I'm going to use a nested for loop. So I'm going to say for I in range of length of palindromes, and then I'm going to say for j in range, I, starting at I, going to length of palindromes. And I'm going to say our remainder is going to be n minus palindromes I, minus palindromes j, in fact. Okay, and then I'm going to say if the remainder is a palindrome, I just then want to return the tuple. So I'm just going to say return palindrome I, palindromes j, and remainder. Okay, so why are we doing this? So first, we start by looping over all the pairs of palindromes. And then here, we're going to calculate the remainder that we need to reach n. Essentially, we want our 3 palindromes such that a plus b plus c is equal to n. So essentially, we're just rearranging this. We're saying c is going to be equal to b minus a. And this c is acting like our x from before, right? This is this small little number. Once we remove it from n, is going to give us the 2 numbers which we can just use this code for here. That's what c is in this case. If this remainder is therefore going to be a palindrome, if this remainder is a palindrome, we know that the other 2 will also going to be a palindrome. One other thing is that because once again we're starting from the beginning, we're going from the beginning of the palindromes, we only need to return I, the current I. We don't need to do any more checks because we only care about one decomposition. And we care about the smallest possible decomposition. Sure, there could be many more possible combinations of numbers, but we only care about the smallest one. And the smallest one is going to be the first possible combination because that's when we have the smallest possible n. And just notice one more thing, j starts from I, not 0, because we want to get rid of any duplicates. So that's pretty much it. That's going to work for 3 palindromes. This is going to work for 2 palindromes. And we also have a case where it's already a palindrome, but we can do one more really quick case. We can just return none. If the number we're given cannot be expressed as 1, 2, or 3. But actually, now I think about it, I can just get rid of that because I know that every number can be expressed, every number in the whole world can be expressed by either 1 palindrome, 2 palindromes, or 3 palindromes. Better yet, actually, any integer can be expressed as 1 itself, or 2 palindromes, or 3 palindromes. And that's pretty much it. All we have to do now is just make sure this is runnable. So we can just say result equals palindrome decomposition, and we can just put our n in there, and then we can print the result. So the final thing now is to go to our test cases. So I'm just going to speed run through this. Okay, so I've just come to the last two now. These are the last two test cases. Nice. And we try the last one. Wait, let's just see if that's right. Yep. Okay, cool. Now let's try the last test case. This should be the hardest. And there we go. Cool. That's all the test cases. That should give us 1, 2, 3, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22. That should give us 22 marks. And then you get 3 additional marks. Program inputs 1 number. I hope they're not asking for user input, but there you go. That program, this enters 1 number. For each one, for each test, 1, 2, or 3 numbers output. Yes, cool. And all tests terminate without crashing / hanging. Yeah, all tests terminate, and there is no crashing. That is good. So there you go. That is question 1 of the British Informatics Olympiad. But yeah, I hope that was helpful. Cool.